In this section, we'll briefly talk about logarithms just to get an idea of what they are and what we can do with them for our problems. Well, first of all, logarithms are generally useful, let's say if we have an equation, and again we'll see some of them in applications. Like for example, 2 to the power of x equals to 3. It's impossible to bring them to the same base. So how can we solve for x? Well, unless you want to use graphing calculator and try to graph them and look for point of intersection, the best way is probably to use logarithms. And the logarithms are essentially defined as inverse functions. By inverse, I mean, let's say if you square something, how do you get back? Well, you can take the square root. There's some variations of that. You have to be careful with the square root and so on. But let's say if you add something, how do you get back? You subtract. Well, logarithms essentially do the same thing for exponential functions. So definition of logarithmic function, well, if we have this definition, we call it exponential definition, which is a to the power of x is equal to y. If you recall, this is a definition of exponential function. We can translate it to the logarithmic form, which states as log base a, this is a little subscript that you see, of y is equal to x. So x is essentially the exponent. So logarithms by definition are really exponents, and they follow a lot of the same rules as exponents do. So what else can we know? Yes, we can read it as log base a of y is x. So let's take a look. Let's talk about how we can translate from exponential form to the log form, just as a little warm-up. Say we have 5 squared equals to 25. What it would look like in the logarithmic form? Well, it would be log base 5 of 25 is equal to 2. And so note that the base and the subscript, the base of the logarithm and this base right here in the exponential equation are the same. Okay. What about 10 to the power of 0 is equal to 1? Well, it would be a log of base 10 of 1 is equal to 0. In fact, we're going to learn maybe later, logs of any basis of 1 are equal to 0. Some notation for logarithms. In some books, and sometimes we will see that the log base 10 is the same as the log. So if you don't see a base, it actually implies log base 10, not that it's missing. Also, log base e has its own special notation. We're going to see this more often actually. It's called a natural log, or ln. Okay, so log base 10 is equal to log, and log base e is equal to ln. Those are actually on your graphing calculator, so you can look for them. Although the newer versions, there is actually a way to input different bases. I may do a calculator tutorial later. So again, you can do, let's say, 10 to the negative 1 power equal to 0.1. You can translate it into logarithm again. So it's going to be log. Notice how I'm missing a base, means base 10 of 0.1. Sometimes I put parentheses around the log, sometimes I don't. It's generally the same thing. It's equal to negative 1. So yeah, on your calculator, you'll have parentheses, but sometimes I don't put it. So it's the same idea. Now we can do the same thing backwards. If you have a log base 5 of 25 is equal to 2, you can translate it in this way. 5 is the base to the power of 2 is equal to 25. Okay? Same idea, log base 8 of 2 equals to 1/3, which is a radical actually. 8 to the power of 1/3 is equal to 2. Okay? We can also evaluate some logarithms without using calculator. That's generally true. If your base and then the log is actually the some power of the base. So sometimes I think about it as 5 to which power is equal to 125. If you can figure that out, you can find the answer fairly easily. I set it up as an equation sometimes. Well, think about it. 125, that's 25 times 5, right? So that's 5 to the 3rd power. So the answer would actually be 3. But let's take a look how I define it. Let's say if you put it as x, if you want to do it as an equation, so 5 to the x power is equal to 125. Well, 5 to the power of x equals to 5 to the 3rd power, so x equals to 3. I'm basically justifying, but the power is 3, and that's what the log is, so that's the answer. Okay, what about log of 10,000? Remember, if we don't see the base, that actually means 10. So 10 to which power is equal to 10,000. Easy way to figure this out, if you count the zeros, you'll notice how it's power of 4. Well, you still need to figure this out. So again, I set it up as the x, I show it as 10 to the 4th power, so it's 4. Or you can just do it just by looking at it. What is a ln of e? If you recall, a ln is a log of base e. So it's really e to which power is equal to e. See how I have it as x? We don't know what it is yet. Well, it's sort of obvious. If it's just e, then it's 1, right? So x equals 1. Another way to look at this, that ln and e are inverse functions. By definition, they cancel each other. Not literally, but they do cancel. They negate each other. So the answer is the exponent of e. If we don't see the exponent, we assume it's 1. So the answer is 1. So see how I notice answer is 1, or ln of e is equal to 1. Okay, let's take a look at another example. Ln of e to the 5/3 power is 5/3. It's the same reasoning as above. Alright, now let's look at some applications using logarithms, or maybe some more involved applications using exponentials. So here's the population growth. That's one of the most common applications of exponentials or logarithms, actually. So here we have the situation from the US Census Bureau that has reported that the United States is becoming more diverse. Here is the projected Hispanic population, that's in millions, that is modeled by this equation right here. Okay, let's answer some questions. So t equals 0 corresponds to 2,000, and the t is between 0 and 50. So let's estimate in what year the Hispanic population will double the 2005 population of 42.69 million. Well, let's not overanalyze the 2005 right here, but how do we know how to double the population? Well, let's take a look. First, we can double the population. It's 85.38 million. And so the question is really, in what year would the population equal to this amount? So I set the equation equal to, so here is where the y goes to, this equation on the right. And here we're going to use some ideas from exponential functions and also using logarithms in order to solve this. The best way to solve it is to isolate this base right here, which is 1.021 to the power of t. So what we want to do is divide both sides by this number, 37.79, because we want to get rid of it before we can solve for t. So notice I divided it round as little as possible. I added about 5 decimal places after the decimal. You can do more if you like. You can use the answer feature on your calculator. So try not to approximate too much, or your answers may be off, which can cause some aggravation later, or will cause you to be off a little bit. But I noticed 5 decimal places usually works, but again, try to have as many as you can. Then how do we get this t down? Well, one of the properties of logarithms, you can actually use any log. I liked a ln because we're going to see e later. So I took both sides off by ln, or like I said, any other log. So what happens in this situation is one of the properties is that the exponent comes down on the front of the ln, and it looks like this. This is one of the properties we're going to need, that a log of, so exponent of exponent essentially is multiplication of exponents. If you think about power of a power, let's say 2 to the 3rd power, and then you square it, it's going to be 2 to the 6th power. So it's really a multiplication of exponents. So how do we do this? Again, the exponent comes down. Now it literally becomes a multiplication problem, so we can divide both sides by a ln of 1.021, and this is what I did. This is how I put it in the calculator, and I got 39.2, or I rounded to the nearest year, which is 39 years approximately. Okay, so it was in 2039 is where it will be approximately this amount. Okay, so that was using exponential functions, and we used logarithms in order to solve for the exponent. In the next situation, what if we have an application using an actual logarithm, which can happen as well if you're looking at ratios, like in this example. So here is the situation. The number of years, which stands for NR, since the two independently evolving languages split off from a common ancestral language is approximated by this equation. N of r is equal to negative 5,000 ln of r, where r is the proportion of the words from the ancestral language that are common or similar to both languages now. So find the following: n of 0.9, which is basically, I plugged it in. Notice I did not use parentheses, but in your calculator you may want to use parentheses around the ln. So I got 526.8, where I rounded to the nearest 10. Some of them are nearest 10, some of them are nearest 100. Remember, you got to be careful you approximate it. Hopefully in my math lab they specify, but let me know if you're a little bit off. But it's about 530 years, so it's been a few years. Okay. Now here is a similar question, but what if it's given in words? Let's say, how many years have elapsed since the split if 70% of the words are similar? So we can write this 70% as a decimal. It's sort of like the rate problem from the previous section. So n of 0.7, I plugged it in and I got 1783. Again, we're approximated. This one's to the nearest 100. Because a lot of times, like carbon dating and, we're just approximating. So it's 1800. And now here's the other situation. What if they found about 1,000 years ago? So here you know the age or the number of years. How can we find r? So it's the opposite situation. So what I did was I divided both sides by negative 5,000. I got negative 1 over 5 equals to ln of r. How can we solve for r? Well, the best way, if you have the logarithm, translate it back into exponential, and that's how you can find r. So if you remember, the base of ln is e, and the negative 1.5 is the exponent, and it equals to r. And so you can put this in your calculator, and you'll get 0.8, which is about 80%. And that's it for this section.